Radon comes from the radioactive decay of radium naturally present in the soil and rocks of the Earth's crust, mainly in granitic and volcanic ground. It is a colorless, odorless radioactive gas that is ubiquitous at widely varying levels on the Earth's surface. It is rapidly diluted in the free atmosphere. On the other hand, it enters buildings through leaks at the interface with the underlying soil and may be found in higher concentrations inside buildings than outside due to the confining effect of the indoor space. The risk associated with radon exposure is an excess risk of lung cancer. It is the second known cause of lung cancer mortality after smoking. As elevated indoor radon levels arise because of the way we design and use buildings, they are man-made even though radon itself is a natural radioactive gas. According to the Euratom Basic Safety Standards of the European Union, the recommendations from World Health Organization and from the International Atomic Energy Agency, it is relevant to carry out radon indoor measurements and to take corrective actions on the building if the results exceed the reference level of 300 becquerels per cubic meter, and to reduce radon exposure as low as reasonably achievable. There are several ways to protect a building based on the following two principles. On the one hand, limiting the entry of radon from the ground. On the other hand, diluting its concentration in the building. Also, the types of corrective actions can be grouped into categories of techniques. Improving the air tightness of the interface between the ground and the building. Checking and improving the ventilation of the building. Improving or restoring the ventilation of the basement or crawl space by natural or mechanical ventilation, or even setting up a soil depressurization system. Each building can be a special case with its own characteristics and those of its immediate environment. An expert assessment or technical diagnosis of the building will enable the adaptation of effective corrective actions to a given building on the basis of the principles previously mentioned. The purpose of the expertise or technical diagnosis of a building is to enable corrective actions to be chosen, depending on the radon level initially measured, the characteristics of the building and its environment, taking into account their impact on the building and its use. This involves carrying out a methodical inspection of the building and its immediate environment to adapt the principles of corrective action to the case under consideration. Based on the prior information collected concerning the building, year of construction, description, plans, photos, sketches, possible renovations or refurbishments, an on-site visit will be carried out. The purpose of this visit is to confirm this initial information, to deepen the knowledge of the building, particularly with regard to potential radon entry routes and its ability to integrate appropriate corrective actions. In this context, it will be appropriate to have an exchange with the owner in order to review all the relevant elements of the building. This may be the type, the nature and the layout of the building and the substructure, the identification of the various service connections, water, electricity, gas, etc., the ventilation and the heating equipment, etc. A questionnaire may be used for this exchange with the owner. The building visit will then focus on various specific points, including the type of foundation and the level of ceiling with the ground. An important point is the identification of the different service connections of the building connecting it to the ground, the peripheral airproofing of existing services, electrical ducts, but also any older service connections. We will also look at the air tightness level of the lower floor, the cracks that may exist, but also the possible passages between basements or crawl spaces and the occupied spaces. This can be trapdoors, cellar access doors, chimneys, etc. We will also look at the level of ventilation in these basements. An identification of the different components that allow the ventilation of these volumes will be conducted. Windows, skylights, hatches, openings, air inlets, etc. In the same way, a very important point is to be able to evaluate the level of ventilation of the occupied spaces. Here again, this means identifying the different components that allow this ventilation. These can be ventilation grids, air inlets, extract units, And it will be very important to check the correct running and dimensioning of the entire existing ventilation system. We are currently in the basement of the building, in a room that we want to renovate as a music practice room. Right. This is very interesting, because it could be an opportunity to combine this renovation with protection against radon rising from the ground. It will be important to ensure the best possible airtightness of the lower floor. For example, on this existing technical shaft, it will be wise to dismantle it in order to carry out sealing work at the level of the service connections. It will also be necessary to ensure good air renewal through ventilation. I see that you have an existing system. It will therefore be necessary to check the performance of this system and to adapt it if necessary. Okay, ventilation is planned to be dealt with in the renovation phase. That's perfect. It will therefore be important to ensure the consistency of the renovation work and of the corrective actions with regard to radon rising from the ground. As soon as renovation work is planned in a building, it is important to integrate the corrective action approach associated for its protection against radon ingress. Thus, at the end of the visit, the analysis of all this information makes it possible to assess the impact of the various characteristics of the building and its environment on the presence of radon, and to provide the necessary elements for the development of corrective actions adapted to the case under consideration and prioritized according to their potential effectiveness and the constraints of the project owner.